for today, we're going to take this like idea of base exponential graphs and then we're going to apply our transformations to them. Okay? And so yesterday we saw a bunch of different exponential graphs depending on the base. And then we're just going to transform them using our normal transformations. Okay? So what you'll see is the general form off to the right with a little description as to the components and what we're going to do off to the other side on the left. We're just going to describe like how the A value, K value, D value, and C value affect the original graph. Okay, it's the same transformations we've already done. And we're going to do this again in trigonometry.
Where is the K value?
The K value is right in front of the bracket. I know it's a little blurry. It's that K value. It's the same K value from before. I know, sorry, you guys don't know cursive. I just grabbed the picture off of Google. Okay, so the A value affects what? X or Y values. X or Y values, which one?
Y.
Well, which one is it?
Y.
No, silly. It's the vertical stretch. Vertical stretch.
It says X right there.
Oh, reflection in the x-axis. Sorry, fair enough. That, okay, to Lenny's, she's not wrong. That does, if the A value is negative, like with quadratics, what happens?
Reflects.
It reflects.
That's what she
Reflects where?
Over the x-axis.
Over the x-axis. Okay,
Flips.
so fair enough, but halfway there. Okay, so it affects the y values. And it affects the y values, to Lenny's point, like when I reflect a graph, we're making all the y values of the original negative. Fair enough? The K value, what's the K value effect?
Oh.
The X value.
Yeah, the x values, right? So it says it's a reflection in the y-axis if it's negative. That's a horizontal reflection, right? So that's going to be affecting the x values. What about the D value? And again, it's the horizontal translation, left and right. Horizontal translations affect the x values. And the C value is the vertical translation that affects the y values. Does that seem reasonable to everybody? It's the same work we've been doing. We're going to see this come back in trigonometry when we start graphing sine x and cos x and then transforming them. Okay, you will also be responsible in trigonometry for coming up with the equation that represents a word problem. So that's going to be like putting all your transformations onto a sine or cosine graph to fit the situation that they're describing. That's where trig gets a little bit wild. But same thing here, right? Tomorrow, we're going to take a look at, here's a situation, which exponential equation should I pick, and then alter to fit the scenario that is being presented to me. Same sort of thing. Oh, Gabe?
And just to clarify, B just represents like the base. Or
The base number, yeah. So if it's like almost like the parent graph. With exponentials, we don't have. There's a bunch of exponential base graphs, depending on what that base is. So we saw yesterday if it was half x or if it's 2 to the x or 3 to the x, they were all what we would call like base graphs, if you will. And then we're going to transform those using all of our transformations from before. Okay? So let's go down here and just take a look. I just want you to state the A, K, D, and C values for each of these, and then write out the corresponding mapping statement with what we would do to the original graph to transform the points. So let's start with the A value. What's the A value here? Gotcha. Dylan, it's 1. Here, Brandon, come your way. The base, the B value is 2. But there's no number out front, and so the A value is 1 in this question. This is B. So that is the base graph here would be f of x is equal to b of, or sorry, b, 2 to the x is the base graph. and then we're transforming that base f of x is equal to the 2 to the power of x. We're transforming it using the transformations that are depicted there. Okay. So that's one trick. There's another trick in this question, which I guarantee you've forgotten about, most of you, but some of you maybe not. I am interested in, well, the k value's there. What's the k value? Why does the k value should be fine for everybody. What is the k value? Everyone agree it's 2? Okay. Everyone agree the k value is 2. Okay. Now, what else? Let's look at the c value now. Sorry, the d value. The one that's still in the exponent.
6.
Ha! Owen?
-3.
Dylan?
Positive 3.
What's happening? Which one is it? We got 3 different answers. 3 answers. Okay, let's rewrite the function. Because we remember from our transformations unit, I can't see the horizontal translation unless x is by itself. So let's rewrite this function.
Oh.
So, what is the c value?
D value.
Sorry, the d value. Sorry, yeah. What's the d value? It is not -3.
Positive
It's +3. And I will reference you back to the originally, like the general form of this. It appears as a minus sign in the original. So the d value is exactly what the number is. This is still a game of opposites. This is like the inside of the function, if you will. Right? So we know that that's going to get moved to the right 3 units. Because it's always opposite of what you see sign-wise on the inside of a function. Okay, what else? Now let's do c value. What's the c value? 5. Everyone agree? Okay, so let's write the mapping statement then. So the transformation okay, x values. How are the x values changing? Let's take a look at our list and our little recall at the top. So the a value affects the y. So I'm dealing with x right now. So which of the 2 variables am I looking at? Or control factors, k and d, right? Everyone agree? K and d are the ones that affect the x values. So somewhere in this component, I've got to incorporate the k and d values into how the equation or how the graph is going to change or how the points are going to move around, right? So k is going to be your horizontal stretch or compression. And remember, it's always opposite of what we think it is. So what do we think it is right now? Or why don't you just tell me what it is? Don't answer that question. What is it? Is it a horizontal stretch or is it a horizontal compression based on the fact that the k value is 2? Dylan?
compression.
It's a compression. It's a compression by how much? 1/2. Right? So we're going to take our x values and I'm going to cut them in half. And then what?
Add 3.
Then I'm going to add 3 because the graph's going to move to the right 3 units. Okay, so again, that's k and d are, oh, craft dinner, there you go. That must be why they picked those variables. Perfect. Okay, what about the y values? How are the y values changing? Is there any vertical stretch or compression with this one, Gabe? Nope. No. So like we're just gonna get a solid y and there's no component in front except 1 because the a value is 1. And what happens to the graph vertically? Is it moving up or down? Up. Everyone agree? Up. And it's going up by how much?
5.
Up by 5. So there's your mapping statement. So you can input any value. Like if you recognize, yesterday we would have done some work, which is maybe why I'm encouraging to go back and take a look at the base graph of y equals 2 to the power of x. You take a look at what the base points were, and you could input those base points into your mapping statement and produce a new graph. Does that make sense? Both x and y you'd put into your mapping statement, and they're going to spit out new x values and new y values.
What do we do with the first part if it's exponential growth or decay?
Oh, sorry. We didn't talk about that yesterday. Okay, exponential growth or decay. What do you think is happening in each of those situations? Sorry, I forgot about that. Growth would mean as like the x values increase, so do the y values. Would everyone agree? So the graph would look something like this. Like in a growth situation, the graph would look something like this. Conceptually, that makes sense. As x increases, so do the y values. Everyone, that's okay? That's growth. What do you think decay looks like? Down would be the exact opposite, right? So as x increases, y decreases. Does that make sense? So that's decay. Sorry, I'll put that somewhere. I don't know where to write that. I didn't leave a spot for that. The back of the lesson, I think, is blank. So we can just slot that down there. Okay, so that's good. That's a little reminder. So anyway, give me an example of something that's growth then from your work yesterday with Desmos. Sylvie?
2x.
Yeah, so like the first example is going to be growth, right? Something like f of x is going to equal 2 to the power of x. And something like decay. What was an example of an equation that would be exponential decay from your work yesterday? Owen?
F of x equals a negative 3 power.
-3 would be a vertical reflection. That would be, I think this.
Yeah.
Sorry. It would be the growth equation, this one, reflected vertically. So it would be like this. That's not exactly what I'm looking for.
That's true.
You know what I mean?
Yeah.
So Owen's saying something like y equals 3 to the x and y equals -3 to the x. It's not quite what I'm looking for. So you would have had some experience yesterday with the slider and sliding the b value around. And there was a point in time, specifically for when the b value was, like we get decay questions. I remember seeing that yesterday.
Oh, yeah.
What does this mean in language?
B has to be greater than 0 but less than 1.
Yeah, so that just means something between 0 and 1. Like, for instance, the next question, which is why these are here the way they are. That'd be an example of a decay question. Everybody okay? You should have seen that yesterday. You would have seen the graph like flip across the axis, right? And become the opposite looking as you slid the slider around. Okay, so the first one, now that we've had that conversation, now we can say this can be growth, exponential growth, and subsequently over here, this one's going to be a decay question. Okay. Let's make a little list here and then we can graph them and then the lesson's pretty much over. Okay? And again, like I wouldn't mind seeing the original graphs. Okay? Like the base graphs that they're asking you to graph and then transform them. Just like before. Okay? Okay, A value for the second question is 3. Good. Okay, so A is going to equal 3. The base in this question, the B value is 1/2. What else? Let's go to the next one. The K value.
1.
It's 1. C. What's the C value? Hadley? It's -1. Good. Right? And again, I'll bring your attention the base the general equation. It's negative on the inside originally. And so the only way to get a plus sign here is if D, oh, sorry. I don't know why that's so funny, eh? I'm going in alphabetical order, sorry. It's D, the D value, sorry. NKC, that could be it too, I guess, isn't it? Okay. So D is going to be -1 because the only way to get a plus sign in there is if D is -1. Okay, and then what about C? It's 0. There is no vertical translation for this graph. Okay, so again, let's just write our mapping statement. So the transformation of the original xy, we're going to use what's happening. So again, K and D are the factors that affect X. Okay, so those are the ones I'm looking at. So I don't really have any horizontal stretch or compression here. So I just get the plane X. But there is a translation horizontally. And what is it? Yeah, so it says +1 in the equation, but we know that that means that the graph is going to move to the left by 1 unit, right? Which means all my x values, we're going to subtract 1 from all my x values, right? In order to move the graph left, I have to subtract 1, right? So that's x minus 1. And what about the y values? There's a vertical stretch there by a factor of 3. So we're going to take our y values and multiply them by 3. And then what? That's it. That's your mapping statement. Because there is no vertical translation for this question. Okay? Okay, I would say maybe, I get the point when we graph these, like 3 points is probably lots for this. Okay? If we need a refresher from yesterday, as probably most of us do, if our graph is f of x is equal to 2 to the x, and if I input like -2, 0, and 2 maybe, those are probably good. You get the idea. Does that make sense? Is that enough for everybody? I think that's okay. So if I input -2 into my equation, I should get -1/4. Everyone agree with that or no? Okay, if I input 0 into the equation, what do I get? 2 to the power of 0 is what? 1. And what's 2 to the power of 2? 4. Okay. So that's just a reminder. Those would be like your key points for your base graph. Okay, and they're going to change depending on. You're just going to have to be a little bit careful with what the base is with these questions when you go to graph them, right? So I know 0, 1 is an original point. 2, 4. And -2 and 1/4. That's probably good, I think. That gives us a pretty good graph. So that's f of x. Okay, and we'll plot g of x will be the transformed one. We'll call it g of x. It's going to be that other graph that's there. Okay, so what has to happen? Gabe?
We input.
Oh yeah, you could. Okay, so I know where Gabe's going to take these points and input them into our mapping statement, which is, you're more than welcome to do that. That's okay. And that could very well be the best way to do this. Okay, okay, Gabe, let's do that. Okay? I'm okay with that. So if I input g of x in there, or the points of the original into my mapping statement, I should see what? When I input 2, I should get 1/2 times 2. Sorry, -2. We'll do that first one. -2 plus 3. And 1 times -1/4 plus 5. That'll be my new point, right? That's the transformation of -2, -1/4. That's what it's going to transform to. So what are the points there? I know that's a little tight. Sorry. Again, this is my first go here doing this. Gabe?
X is 2.
Yeah, that sounds right. You get -1, right? This 1/2 times -2 is going to be 1, and then plus 3. That sounds like 2 to me. And then -1/4 plus 5 is what?
No, because you times 1/2 by
No. He's right. Yeah. Sorry. The output for that one is +1/4. Sorry. Not -1/4. Sorry. Nobody caught that till now. Well, you know what this? We know it's positive because we drew it here. I just didn't write it positive in my table of values. Okay, so what's -1/4 plus 5? Oh, you're right. Sorry, I'm sorry. You're right. I see the confusion. Okay, so what is it then? 5.25? Okay. So that's where that point goes, right? Based on the mapping statement. And I can do this with the other 2 points as well and see what happens, right? So let's see what happens. The x value, when I input 0, I get 1/2 times 0 at plus 3. That sounds like 3 to me, right? So I get 3, and what happens to the y value when I put 1 in? 1 times 1 plus 5 sounds like 6, right? What is happening is I'm taking each individual point and I'm inputting them into my mapping statement like we've done before. It's a little bit different, but not quite. Man, hopefully there's a recurring theme that like the mapping statement is a very robust method because it doesn't really matter what equation you're working with. If you can identify the factors that control what's happening to the graph, then you can use the mapping statement and input the original points and get new points out. It's a pretty good way to do it, right? I'll do the second one with our like moving points around on the grid, but either or of them is going to be good. Gabe?
Never mind. I just
We should get 6, right? Does everyone agree? When I input 1 for the y value in my mapping statement, 1 times 1 plus 5 should be 6. And the last one should be, this is a very nice question actually. 1/2 of 2 plus 3 is going to be 4. Everyone agree? And it'd be 9 for the y value. If I input 4 into my mapping statement, I get 1 times 4 plus 5 should be 9. Everyone agree? So you can go plot those points. That's your transformed graph. Based on the transformations that we identified from part 1. So you just plot those points and you've got your graph now. What's happened to it based on the conditions that have been put on that base graph of y equals 2 to the power of x. So 2.5 and 5.25. Okay, and then 3 and 6. Let's see if this fits. I hope this fits. It does. Perfect. 1, 2, 3, 4. That's not bad for a question I made up this morning. First time graphing it right there, kids. getting to be good at my job until the wheels fall off. All right. How do I connect those? I just connect them. That's going to be the graph of g of x. It's going to be in red. Okay? Okay, domain range. That might not have been the best connection of dots. Let's just do that again. Okay. Domain. Do we have any restrictions on the domain for an exponential graph?
No.
The answer is no. So our domain should look something like this. Okay. What about the range? Is there a restriction on the range?
Yeah.
What is the restriction on the range?
Y is part of the real number such that y is greater than or equal to 5.25.
5. So remember that the tendency is I continue to put in more and more negative values of x, the graph is going to approach but never touch a value of 5. Okay, so this is going to continue to get closer and closer and closer and closer and closer but never touch that value of 5. So horizontal asymptote of y equals 5 would be the equation.
But it can't be y. It can't be greater than or equal to. So it's just greater than.
It's just greater than 5, yeah. So it's going to be y as a part of the real numbers such that y has to be greater than 5. Because there's a horizontal asymptote here. How do I know it's there? Just out of curiosity. Where was it originally? It was originally at y equals 0. And then we took the base graph and transformed it vertically, translated it vertically, 5 units, which means the asymptote went with it, 5 units up. Okay? Okay? Do another one? Okay. We'll do this one without the mapping. Well, the mapping statement might be honestly the best way to do these questions, as you can see. Okay, base graph, please. What's the base graph? Yeah, 1/2 of to the power 1/2 to the power of x, 1/2 x. That sounds like a line to me, which some of you would have experienced typing in the Desmos yesterday. When you just type in 1/2 x, you just got a line. Yeah, it's just got to go like that. Okay, so let's plot that. What did that look like? It should be what? It should be a mirrored image of the graph we just did, the black one from the last question, which is what we saw yesterday, which is why I'm telling you, if you didn't do yesterday's stuff, go do it. Okay, because you'll get to see it. You'll watch it just flip. And it becomes a decay question when the base becomes something from 0 to 1. Okay, so we should see 2 and 4. 0, 1 is still a point, and then we should see the positive 2 and 1/4 this time.
Bless you. Who said bless you, chat?
Okay. There you go. That's a pretty good graph right there. Okay, so now we need to do a bunch of stuff to it. Like what? Let's I'm gonna avoid the mapping statement this time. Let's do the stretches. So vertically stretch by a factor of what? 3. Everyone in agreement? So I'm gonna draw a blue graph here. That's the black one vertically stretched by a factor of 3. That's what I'm gonna do right now. So we are at, oh boy, that's not gonna work. You guys got me. Here, let's change it. Let's change it to a 2.
Why can't we do 3?
I don't think it fits on the grid.
Well, it partially does. It's like right at the
I need 12 boxes. You just change the 3 to a 2 for me. The 3 from the original question, just change it to a 2, and then it'll fit. Almost. They're not gonna mess you up. You're fine. So vertically stretch by a factor of 2, not 3. I'll change that later. So this point that's 4 units away from the y-axis is now going to go to 8.
Wait.
What?
Mr. McKay.
What?
It's x minus 1, so when you put in the negative 2, it goes to negative 3.
Yeah, I haven't done the translation yet. I'm only doing the vertical stretch. I'm doing one graph at a time. So I gave you a contrast between methods here too, right? Just so everybody's clear. So we can use the mapping statements, which seem to work very well. I don't know if that was just a coincidence with how I wrote the question. But I'm also going to give you the translation work that we did before too. Okay. So that is now, the blue graph is going to be f of, so we'll call it g of x. G of x is equal to 2 to the 1/2 x. And then Gabe, what do we have to do?
We have to translate it left.
Okay. Left one. So we're gonna have one more graph here, which is gonna be maybe a little bit tight. This is gonna be your final graph. Okay, h of x is going to be this one. Okay, where h of x is equal to 2, 1/2 x plus 1. Also, don't forget to label your axes, as I did. Okay, domain range. Any restrictions on a exponential graph for x's? No, you can input any value of x into an exponential and not have to worry about anything. So that's pretty common for the domain. The domain for an exponential graph is always just going to be xer, or x is a part of the real numbers. But the range here is what? Gabe?
The range is y is an element of all the real, so all the part of all the real numbers such that y can't what it, because the 0.25, what did that go to exactly? Was it 0.75?
So let me ask you a question, because this is pertinent to everybody. Did we vertically translate the original graph? Was there any C value with this question? So if there's no C value with the question, then the asymptote, or that's not an asymptote. It's the value, well, it kind of is an asymptote. The value, it is an asymptote. The value of the graph, the y values of the graph are going to continue to get closer and closer and closer to 0, which is the definition of an asymptote, without ever touching. And so because I did not have a C value, I did not move that asymptote. It's still there at 0. And so the graph is going to be y still has to be greater than 0. That only changes if you move the graph vertically. Okay? Is everybody okay? Glad we made that clear that it's an asymptote.
Took it back